Hi guys, in this video we'll begin our look at resonance. Resonance is covered early on in most textbooks. In the Klein textbook it's covered in chapter 2, but also some of the information is discussed in a later chapter 17, or actually chapter 16 in I think the most recent edition. Now, resonance can also be called delocalized bonding or pi bonding. We'll see what delocalized means. Pi bonding, we can clarify that by stating that resonance involves only pi electrons. And actually, in the golden rules at the back of the handout, I think the very first rule reminds you that when we do resonance, we're only going to move pi electrons. Okay, this first page is a good amount of theory that we need to introduce. Then we'll move on to really drawing resonance structures and actually doing the resonance. To introduce the theory, we'll be looking at neutral conjugated alkenes. That's actually a little bit tough as a beginning molecule because they're neutral. We'll see that resonance can be a little bit easier once we get to cations and anions. Because of the discussion, the questions and answers become a little bit more intuitive. But let's set some of the foundation first. Let's first look at the stability of conjugated dienes versus non-conjugated dienes. These two molecules here. And if you look at the heats of hydrogenation numbers, we see that this molecule here is more stable. They're both hydrogenated to pentane, but this one gives off more energy when hydrogenated. Thus it contains more energy. Thus it's less stable. And we see that from the H of H numbers. So why is the conjugated diene more stable? Well, first off, what do we mean by conjugated? It's actually the two alkenes are conjugated of the diene. We have pi bond and pi bond. One electron each makes pi bond there. One electron each makes pi bond there. And so we have orbital overlap between these two carbons, p orbital overlap, and p orbital overlap between the other two carbons. But we also have some p orbital overlap between the carbon 2 and 3. And so we have pi bonding between the center two carbons as well. Now our original structure, right, I drew on it. The original structure looks like only between carbons 2 and 3 there's only a sigma bond. And it looks like there's no pi bonding. Yeah? Well, that's just incorrect. And this is our first example of whenever we have resonance, and that's what you have here, a given Lewis structure does not adequately show the pi system and the pi bonding that's going on. We have to understand more of the theory to understand that there's pi bonding between carbons 2 and 3. So we have an inadequate Lewis structure. Now we say that these 4 p orbitals are all conjugated. Or I'll say all aligned. They're all interacting, sort of like toy soldiers lined up. Aligned / conjugated. Now we can compare that to the other diene. It's also a diene, 2 alkenes, but the alkenes are not conjugated. This one has an alkene here, or a pi bond here. One electron makes pi bond, as we see. Pi bond over here, we can draw it in. One electron overlap makes pi bond. But the center 2 are not overlapping. And we can also note, importantly, that the center carbon here has no p orbital. And because there's no p orbital there, the continuous overlap of the 4 p orbitals is not present. We have sort of like a break in the chain. And so the alkenes not conjugated, we have 2 separate pi systems. You've got the alkene here. We can call that a pi system because it involves 2 p orbitals. The alkene here, a second pi system, and they're not linked together. They're not conjugated. But over here, they're linked together. And we have 1 conjugated pi system. Now, why is conjugated more stable? Well, we have additional bonding. Hopefully you agree that more bonding is a good thing, and it usually is until we say it's not in organic 2. But the additional pi bonding here between carbon 2 and 3 is a stabilizing effect which lowers the energy of the molecule, and we see that in the H of H number. The non-conjugated diene does not have the additional pi bonding between these 2 p orbitals. They're too far apart. And usually if we have an atom in between that has no p orbital, the 2 p orbitals on each side will be too far apart to interact. Okay. I also want to introduce you to a cumulated diene. There's 2 alkenes here. It's kind of odd looking. The center carbon is sort of double bonded on each side. Cumulated. Now this is not conjugated. All right? 2 separate pi systems here. Alkenes not conjugated. Students often think, well, these pi bonds are so close together, they must be conjugated. No. We have to understand that, I'll show this, try to show this with some orbitals. The pi bond on the left, if we show it like this, Well, the center carbon is sp, and so it has two p orbitals. All right. But there we go. Let's do like this. That center carbon has two p orbitals. Let's first draw it here. We have carbon, carbon, and carbon. P orbital here, p orbital here. One electron each overlapping. But there's another p orbital in this carbon. It's perpendicular. Okay? It's going straight back. Thus, this one over here, to be able to interact with that one, and it does interact with that one, it's also going back. And you have one electron each pi bond. So the center carbon has two, it's sp. These two are interacting to make pi bond over here. These are the two p orbitals on the center carbon. They're perpendicular to each other. And so the one on the right, its p orbital is going to be like that, and it's actually interacting with that p orbital. And so you have two different pi systems. These two are lined up. Okay, 1 and 2. For any other p orbital to be lined up with those, it needs to be like that. Okay, now we have 4 lined up. Disregard the color. But if these are turned 90 degrees, these two are not lined up. That is, these two are not conjugated with these two. This alkene, this pi bond, is not conjugated with this pi bond. If you use your basic understanding of structure to then understand this idea. Okay, now this is benzene. Benzene's a fully conjugated cyclic system. This is our definition of aromatic. Each atom has a p orbital and they're all interacting. I'm not going to take time to do that. You can draw all 6 p orbitals. They're all 6 interacting. If we had I don't have 6 red ones, but I could show these all. And I don't have a 6th red one, but there we go. I set these up. They could have been turned perpendicular, but all 6 around that ring are interacting. Okay. Now in the structure, it looks like I have pi bond here, pi bond here, and pi bond here. All right, only here. But does that mean that there's no overlap between these two? Why are we saying there's overlap between these two but not these two? Okay, well that's just not right. There's equal overlap between each of these. There's equal overlap between every 2 here. And so we can also draw the structure with pi bond here, here, and here. Well, these are just resonance structures, where all we did is move pi electrons. And the true structure is actually you have overlap all the way around. And we call this our hybrid. Now just put that in your notes for now. Once we move forward, you can refer back to that. But you can't really introduce conjugation and resonance without at least mentioning benzene. Now benzene will be covered in more detail in Organic 2 when we cover aromaticity. Okay, closer look at conjugation found in conjugated dienes, number of p orbitals in the conjugated system. We actually already answered that. 4 p orbitals. Okay. Number of pi electrons in the system, well, each one has 1, right? Basic structure. And so there's 4 pi electrons. I'm actually going to skip the molecular orbital view for now. It's a generic discussion to begin with. Let's stick to some specifics and maybe see if we can work our way back to this. But let's refer to this up here again. We have electron overlap, p orbital overlap, all the way through this molecule. Okay. At this point, though, let's start thinking about drawing resonance structures. Now it's a touch difficult here because there's no heteroatom, and thus we have no dipoles to sort of guide our electron movement. All we can say is that the carbon-carbon pi bond is polarizable, and the electrons can sort of be shifted, and let's just do that. I'm going to take these electrons and move them this way. And that's going to give a lone pair here on the end, and that's a negative charge. And that would leave this without a bond, and that's a carbocation, a positive charge. And this is just a resonance structure because all we have moved is pi electrons. And note that we have a resonance arrow, a double-headed resonance arrow that we show between our different resonance structures. Now at this point we can draw another resonance structure, and the question we can now ask, since we have charges, how do you stabilize a positive charge? Well, the answer is we move electrons towards it. We can move these electrons towards it, but that'll just give us back this structure. Are there any other electrons we can move towards this cation? And the answer is this pi bond. We can take it and swing it over here. That's sort of like a windshield wiper. Over here. Because we may take it back. We're not moving the pi bond onto the carbon as a lone pair like we did here. We're shifting it all the way over to make a pi bond on the other side. And that electron movement leads to, well, nothing changed there. We moved the pi bond over here. We swung it over. It's still connected here, but we swung it over and connected it from there to there. And now this carbon is left without a bond, and it's now positive. Again, all we moved is pi electrons, so this is another resonance structure. Now I could draw more. I could polarize this center pi bond. I'm not going to do that here. When drawing resonance structures, the true structure is a blend of your resonance structures, a composite, or what we call a hybrid. And the hybrid has the same sigma backbone, but we blend the structures together to produce the hybrid. For example, Between carbons 1 and 2, we have double bond, and now single. What is the blend of double and single? Well, it's a bond and a half. A bond and then a half bond. Now, this is actually two double bond, double, and then single. It looks like it has more double bond character. I'm not going to distinguish between, 1.6 or 1.7 or 1.2. This is a 1.5, and we can say the bond order equals 1.5. What's the bond order between carbons 2 and 3? We have single bond, double bond. What is a blend of single and double? Well, it's somewhere in between. We're going to call it a bond and a half. And between carbons 3 and 4, double, single, and single. What's the blend of double and single? Somewhere in between. We're going to call it bond and a half. This gets a little difficult because it's not really a bond and a half, because are these equal contributors? The answer is no. This is your major contributor, and these are minor contributors. Ultimately, our hybrid shows us that we have electrons spread out all the way through here. And there's pi bonding between carbons 2 and 3. And that's very much what we tried to say up here. You have electron density spread out all the way through here, including between carbons 2 and 3. Now the bond order equates to the electron density between the different nuclei. But it also equates to the bond length. And so this is your true structure. If you could look at this diene, you would see electrons spread out all the way through here. Sort of like if you put water in a garden hose, it would spread out all the way through the hose, or in a pipe or something. If you put water in a garden hose, you wouldn't expect some water to be here and then some more water to be here and there none be here. No, the water would flow equally all the way through here. So this structure is inadequate. This is more of a closer to reality structure, but it's a bit cumbersome. And instead, we organic chemists typically draw these sort of fake resonance structures and talk about how they contribute to the hybrid or true structure. Now this one's major in this case because there's no charge separation. Once we start creating charges, this is going to raise the energy of these fake structures. If they were actually discrete structures, they would have higher energy. And so what we can say is this is the hybrid, but it looks closer to this one than to these. Okay. For homework, answer the questions here. P orbitals, pi electrons, bond order for each carbon-carbon bond. Again, theory here. We're building towards a general understanding of resonance. We have to sort of mate a variety of ideas here. We got to sort of work to pull all this together. And we'll do that as we move forward. Now, as we move forward, we'll also be looking at charged molecules. And the first one is look at cations. And here, our electron movement will be a bit more intuitive because we have a charge. Now, with resonance, we can stabilize a positive charge. And it's importantly to understand of how do you stabilize positive? Do you move electrons towards it or away? And the answer is always you move electrons towards a positive charge to stabilize it. And in this case, we can do that by moving the pi bond here, and that would give this resonance structure. Now, by the way, this is called an allylic cation. That's when you have a carbocation adjacent to an alkene. And it's resonance stabilized, as shown here. Now, this is the only resonance structure we could draw. At this point, we can ask, well, which is major and which is minor? Well, they're both equal in energy. They're equal in structure. These are equal contributors. Not major and minor. Since they're equal contributors, that means they contribute both equally to the hybrid. Now, the hybrid has the same sigma backbone, carbon-carbon and carbon-hydrogen sigma bonds. But then we talk about blending the pi bonds or the pi electrons. And between carbons 1 and 2, we have single and double. And the blend of that is actually 1.5. 1.5. And that's actually a perfect blend. Because it's a perfect blend of a single and double. They both equally contribute. Between carbons 2 and 3, we have double or single. Well, a blend of that is 1.5. Again, 1.5. Charge. The carbon on the end left is positive, here neutral. The blend of that is partial positive. On the other end, neutral or positive, the blend of that is partial positive. And this is our resonance hybrid. That's our true structure. If you could look at the allylic cation here, this is what you would see. The electron density between each carbon is identical. That is, this is not correct. It's not pi bond and double bond and single bond. Okay, it's not bond order of 2 and 1. It's actually 1.5 on each side. And so each carbon-carbon is same BO and same length. But importantly here, the charge has been delocalized. The charge is not just on one carbon. Okay? The charge has been spread over, I say it has been spread, we can say the charge is actually spread over 2 carbons, not just one. Now in terms of the theory of the orbital description, we have, well, pi bond, 1 electron each, okay, but the carbocation is also a p orbital. I suspect many of you would not be able to have stated that, but the carbocation is sp2 with empty p orbital. Okay, that's from our test 1 discussion of structure hybridization. And here we see we have 3 p orbitals conjugated, and the system has 2 pi electrons. Now once they're conjugated, they're all interacting, and the 2 electrons are spread out in there. In the pi system, like water in a garden hose that's maybe 3 foot long. And we no longer kind of just put the 2 electrons here. They're spread all through here. And that gets us to, well, the hybrid. And we could talk about charges and okay. Okay. For homework, please draw resonance structures of the benzylic cation. This is where you have a carbocation adjacent to a benzene ring, or more broadly an aromatic ring. In doing this, keep in mind, how do you stabilize a positive charge? You move electrons towards it. In A here, we're doing stabilizing with a carbon-carbon pi bond, and the pi bond here we can move towards it, and we can get resonance structures. But in this case, we can draw additional resonance structures. Please do that. In addition to using a pi bond to stabilize a cation, we can also use a lone pair. And in this example here, we have a carbocation with a lone pair adjacent, and we can move these electrons here and get pi bond here and 1 lone pair remaining on oxygen, and now the oxygen is positive. We can ask major or minor. Well, these are different. And this one here is major. And this is minor. Why is this major? Well, more bonds. We just made an additional bond here when we move the electrons. And so this fake structure is theoretically more stable than this other fake structure. This one's also better because all atoms have an octet. Even the oxygen, which looks a little weird being positive. We might say that's not good. But the oxygen has an octet here, 2, 4, 6, 8. And as long as oxygen or nitrogen or halogen has an octet, it's okay for it to take on a positive charge. But you never want to leave oxygen without an octet, or nitrogen or halogen. I think that's a golden rule. A heteroatom should always have an octet. And it does here. Over here you see carbon has no octet. And so that's not as good as here where carbon does have octet, and the oxygen. Okay, what does our hybrid look like? Well, we have the sigma framework. And the only difference is single bond between oxygen and carbon versus double. Blend of that is somewhere in between, like a bond and a half. We'll clarify that. Charge. Carbon, positive or neutral. Blend of that, partial positive. Oxygen, positive or neutral. Blend of that, partial positive. And here's your hybrid. True structure. If you could actually see this carbocation, well, you would not be so quick to call it a carbocation because some of the charge is actually on oxygen. Actually, more of the positive on the oxygen. Because we identified the major contributor, the hybrid's going to look more like the major contributor. That's analogous to maybe the child looking more like the mother as opposed to the father. Because maybe the mother is more stable. A child can look more like one or the other. In this case, the hybrid looks more like this structure, and we explained why. Ultimately, though, the charge is not just on one atom. It's been spread over two different atoms. The charge has been delocalized. And so this carbocation is much more stable than just maybe this one. There's no resonance here, there's no delocalization. In terms of orbitals, the orbital theory, we have, well, the oxygen's there. The oxygen is sp2 with one of the lone pairs with LP in a p orbital, which you should have been able to state based on test 1 discussion. Anytime a lone pair is next to a p orbital, the lone pair is going to want to be in a p orbital. Well, there's a p orbital here. It's empty. Okay? Just like we stated up here, it's a carbocation. Well, here on this oxygen, we're going to have a p orbital and we're going to put a lone pair there. Well, these are interacting. And now we have two p orbitals with 2 pi electrons. And the electrons are spread out in there, and that's kind of shown like this. Okay, in the next example, I'll let you do that on your own. Show resonance structures here. You can think about the same questions. Okay, the theory, the hybrid. Of course, we have a lone pair here. So show resonance structures here, all that are possible. In this first example here, we only had one additional resonance structure. Down here, you may have more than one additional. Also think about the next questions. This is examples of how resonance stabilization affects regiochemistry of alkene reactions. And so this takes us back to alkene reactions from test 2. And the question becomes, where do we want to make carbocation, top or bottom? Okay. Here, where do we want to make carbocation, left or right? Okay. So we want to consider each possible carbocation. And depending on where you make carbocation, then the bromide can attack either the top or bottom. Same idea here. So think about these reactions here and predict which product should be major product. Okay, as we move forward, we'll look at resonance stabilization of anions. Okay. But we'll pick up here in the next video on resonance. We'll also get to acid-base chemistry. Of course, when acids act as acids, they generate a conjugate base, which is typically going to be an anion. Okay guys, that's the first video on resonance.